Recursion Tree, and we are going to start master method, which most of the students already know. Okay, and anyways, I will share my slides and they can take the content from the slide. And otherwise, if they really they are not able to follow, I can take one more time the class, or maybe you people can discuss among yourself, and it can work out. Okay, so I really cannot cancel the class. So let's continue with this, students. Only 12 students. I feel sad, but I can't help it, because as I told you, uh, it's tomorrow and day after tomorrow, I may be busy in, in some of the events. So I am not sure at all, because that there is no fixed timetable. Anytime the meeting is scheduled, I have to go and join that meeting. Okay, so let's continue with this. Uh, Fine. So today we were discussing in the last class regarding the guessing method, right? Which we also call as um, which we also call as substitution method, right? Because we make a guess, and then by substitution we prove that it is true for any value of n, right? So that is what we call as substitution method. So we had seen some examples of substitution method. So today we are going to discuss, the last example, you can say, of the substitution method, which we call as changing variables. Okay, so sometimes expression is given to me like this, and guessing it directly is little difficult, right? So if it is given Tn is equal to 2t under root n plus log n. So first of all, whenever we apply guess, okay, we can do a guess. It has to be a educated guess, some, not something simple guess. So I have seen many problems of the same kind, and then I can make a guess if I see a similar problem, right? So we have seen problems of similar kind wherein, this used to be, let us say this used to be a constant term, right? It was plus some constant term or some variable of n, let us say. It used to be something like n. But I'm getting a problem wherein this is not n, this is log n. And here I used to get a t n by b kind of a thing, and it is now power of n. I have been seeing something like t n by 2 or t n by 4 or something, but here it is n to the power of half, right? So another method, before making a guess, what we can do is we can apply changing of variables just to simplify it, right? So for changing a variable, let us say we want to again go by the guessing method, but before applying the guess, we change the variable. So I picked this up, log n, okay, and I want to make this as constant, let us say. Okay, so we consider that, let us say that log n base 2 is equal to m. Let m is equal to log n base 2. So if I say like that, that means 2 to the power of m becomes n, right? That means n becomes 2 to the power of m. So now when I put this thing in my expression, so I replace n with 2 to the power of m. So I get t 2 to the power of m is equal to 2t, right? Now n is my 2 to the power of m, so n to the power of half. That means 2 to the power of m by 2 plus log n is nothing but m. So I get my expression like this. T 2 to the power of m is equal to 2t, 2 to the power of m by 2 plus m, right? But this was not the aim. I actually want what the aim was, that I get something like Tn is equal to something that is with respect to n, right? So now rather than calling this as Tn, I call it as Sm, for example. Okay, I call it as Sm. So when I say Sm is equal to T2 to the power of m. Now let us say that rather than calling this as T2 to the power of m, I call it as S of m. Okay, I could have taken some other variable also other than m. So we are saying that this left hand side we will call it as Sm. So now if I want to present it in terms of Sm, we call it as Sm is equal to 2t m by 2 plus m, right? I call it as 2t m by 2. Why m by 2? Because Sm is t2 to the power of m. Okay, so when I say Sm by 2, Sm by 2 will be T2 to the power of m by 2. Okay, so we call it as Sm equal to 2s m by 2 plus m. So we have just changed the variable. So this is what we have got now. Sm is equal to 2s m by 2 plus m. Now, what is the guess? We know this kind of expression, the answer is going to be, we guess it as Sm is equal to O m log m. Right? So if this is given to me, I know my complexity Sm will be O of m log m. So now I replace the term, right? So this O m log m is nothing but O m log m is, I replace m with, m is given to me log n. M is log n base 2, right? So that's what we are doing. So m is log n. Log n, log of m means log of m means log n. So this is what we get, right? So Sm, I get it as O m log m, right? So this Sm is O m log m. So I get, so Tn is equal to T2 to the power of m is equal to S of m is equal to O m log m. Now I substitute m with log n. So we get Tn is equal to O of log n log of log n. So sometimes we require to change the variables. So when to just to simplify the expression. So whenever it is required, we change it accordingly, and the method remains the same. The substitution method remains the same. Okay, so that is just one example to say if we need to simplify the expressions. Okay, so that is what was our substitution method. Okay, now why do we go for other methods or other kind of methods? So we were actually discussing something like that. We saw one previous example, right? In previous example, we saw that if something is O n log n, we saw one example, right, wherein it was O n log n, but you know that the growth rate of n square is more than O n log n, right? So if I guess that it is O n square, it is very difficult to prove that, then I will be able to prove that it is O n square. But if the complexity is O n log n, right? So because n log n is always contained in O n square, it's very difficult to find the right answer that it is O n log n. It's very difficult by the guessing method. Okay, it's difficult. So suppose if I get it as let's say O n square, I'm getting the complexity as O n square, then I have to see that, okay, I am getting it as O n square. Should I try it with O n log n also? Okay, so yeah, let me try with O n log n, and then I get it as O n log n. Then I say, okay, I will choose O n log n, then O n square. But this way it is very, very difficult. We cannot keep on doing like that. Okay, so guessing should be done for similar kind of problems. Okay, so for few problems, I know the standard solution. The solution is O(n), the solution is O(n) square, or the solution is O(n) log n. And if I see some problem, a similar problem which can be reduced to the problem for which I know the answer. Okay, then I say that yes, I am 100% sure that I am going to guess that this is going to be the answer. Okay, so we make the guess for the problems which we have already seen, which we are very, very sure about. And how do we sure about? Only when we have actually seen lot of problems. Then we can make a guess for anything which can be reduced down to that same problem. Okay, but in general, guessing the answer can be difficult. Right? It is difficult. Now, for example, if this is a question, Tn is equal to 3Tn by 4 plus n square. Right. So is there a base that I would have seen the problem that was n by 2 or something plus n or plus Cn square? Maybe it's little difficult to guess the answer. Similarly, if a problem is like this, Tn is equal to Tn by 3 plus 2T 2n by 3 plus Cn. Okay, so for such kind of problems, we go for, we do a guess, but after a while we do a guess. Okay, or exactly what we do is we go for a recursion tree method. Okay, so we find the answer from recursion tree method. First method is the substitution method, or we also call it as guess method. Okay, but it is not only guessing method, right? In substitution method, we guess and then we assume that it is true for some value of k, and then we try to prove that it is true for tn for any value of n. That is what is substitution method. In recursion tree method, what we do is we find the answer by making the recursion tree. Okay, we find the answer by making the recursion tree, and then we verify the answer by the substitution method. Okay, so we first find the answer using recursion tree, and then we verify that, okay, my answer is correct using the substitution method also. Okay, so that is what we call as recursion tree. So what is the method? The method is, there are few steps of the recursion tree approach. So what are these steps? The first step is, we draw out the cost of the tree at each level of recursion. Okay, so you know that what is the recursion or recurrence, right? What we do in recurrence is, you have Tn. Let us say here I am every time doing n by 4, n by 4. So I will keep on doing every level of tree. I will do n by 4. Next level of tree, I will do n by 4, n by 4. I will keep on doing this till I reach to a constant value. For example, if it says that the answer is +1 and there is only one, there is only the number of item n becomes 1 at the end. When I reach to the leaf of the tree, there should be a terminating condition, right? For the terminating condition, let us say the answer is given. For example, you saw in merge sort that there is only one element. Okay, so what we do is, first we draw the recursion tree, and then what we do is, we find out the cost of the tree at each level of recursion. At each level we find out the cost, and then what we do is, we are going to add the cost of the levels of the tree. We are going to add at each level what is the cost. We are going to add up that cost. Now for adding up the cost, right, what do we need to do? We need to find the cost of each level with respect to the depth. Right, we need to find the cost at each level. How do we find the cost? With respect to the depth. And finally we need to find out what is the depth of the tree, right? And we also need to find out the how many number of leaves are there. That will provide me the bound. Okay, so actually if I know the number of levels, right, and I know if I know the total number of levels, how do I know total number of levels? By finding out the depth of the tree, right? Once I know the depth of the tree, I can always find out with respect to the depth what is the cost at each level. I can sum it up. Okay, but for finding the bound, okay, upper bound, I need to know how many number of leaves are there, right? At the end, at the last level, how many number of leaves are there? Okay, so once I know this thing, that these are the total number of leaves at the last level, I know the cost at each level, right? And I add them up, and this number of leaves is providing me the bound. I can find out the complexity. We will see it with the help of an example. Once we do this, then we can always verify our answer using the substitution method. We get an answer, we can use substitution method for the verification of the answer. Okay, so how does it? Let us take this example itself. Tn is equal to 3tn by 4 plus n square. This is what is given to us. Tn is equal to 3tn by 4 plus n square. So how do we present it? We present it as, this is some constant c n square, right? Cn square, we are saying initially, let us say that the depth is 0. Depth is 0. So my cost is, let us say, just some, whatever is given here. So this is the divide cost, and this is for the, you can say, this is the combining cost after solving everything and then combining. So we can represent it as Cn square here, and then 3 Tn by 4, 3 times. Tn by 4, Tn by 4, Tn by 4. So if I add this up, it is 3Tn by 4 plus Cn square. C is some constant. Okay, so this first level we represent like this. And we say that the cost at this particular level, level 0, if you say, root level is Cn square. And next level, the cost is 3Tn by 4. Okay, so like this it is going to come. So I'm writing the cost here. So the cost at this level is Cn square, some constant Cn square. Okay, and this level the cost is 3Tn by 4. Now this n by 4 again I can represent. How do I represent this n by 4? N by 4 again I can write as, n by 4 again I can write as Cn by 4 square from this term, Cn by 4 square plus 3Tn by 4. 3Tn by 4 means Tn by 4, Tn by 4, Tn by 4. So Tn by 4, n by 4, 4 means Tn by 16, Tn by 16, Tn by 16. So this gives me 3Tn by 16. right? Because this, so if I go here, this is Tn by 4. So Tn by 4 means 3Tn by 16. So 3Tn by 16, I am writing as Tn by 16, Tn by 16, Tn by 16. Plus n square means Cn by 4 square, right? So like that we have written Cn by 4 whole square. Like that we have written. Cn by 4 whole square. This is coming from n square. And 3Tn by 4, Tn by 4, Tn by 4 is n by 16. So now if you see, so at this level, if I, so this is how it is going to come. So at this level, if I calculate the cost, it is going to be 3Cn by 4 square, right? At this level, if I am going to calculate, this is actually 9 terms, right? 9 terms of n by 4 square, right? So 1, 2, 3, 3, 3, 9 terms. So I can also call it as so there are 9 terms, which is 3 square, right? And this is 4 squares. N by 16, 16 means I can always call it as 16 square. Okay, so when I calculate the cost, I can call this as 3 by 16 Cn square. This is 3 by 16 Cn square. I can call this as, if I have to call this, I can call this as 3 by 16 whole square Cn square. That you can make out, right? So 3 by 16 square means this is 9 by 16 square Cn square. See, there are 9 terms of 1 by 16 square. So that is why 3 by 16 square Cn square. Right? So this is Cn square. So like that, it will keep on growing. But how long will it grow? Right? So I want to find out the value of D. Right? So this will be, so it will keep on going. So what is the cost at each level? So this is the cost at each level. Cn square 3 by 16 Cn square plus 3 by 16 square Cn square. It's a geometric progression. 3 by 16, where is your R in the geometric progression? Your radix is going to be 3 by 16, right? A is, it is starting with 3 by 16, then every time you are multiplying each term by 3 by 16, right? Like that it is going to come 3 by 16. So at each level, if you want to calculate the cost, it is going to be 3 by 16 to the power of D Cn square. You can just put it at this level, it is going to be the value of D is 0, depth is 0. So it is Cn square. At this level, depth is 1. So 3 by 16 Cn square. At this level, depth is 2. 1, 2. So 3 by 16 square Cn square. Right? Like that, it is going to grow. Okay. So what is the depth of the tree? Can anybody say what will be the depth of the tree? The depth of the tree will be, so how do we find out the depth of the tree? So every time you are reducing the data by 4, right? Every time you are reducing the data by 4. So here it is n, then it is n by 4. It is n by 4 square, right? It is, you say it is 0, here it is 1. The data size is reduced to n by 4. So at the last level, the data size will be n divided by 4 to the power of D. Isn't it? This is, the data size is n here. Next level, it is n by 4 to the power of 1. Right? This side, it is n divided by 4 to the power of 2. N divided by 4 to the power of, every level, it will be 4 to the power of 3. So like that, it is going to be n divided by 4 to the power of D. That is going to be equal to how much? How do we find the depth? N divided by 4 to the power of D will be equal to
1.
1. Yes. Yes. N divided by 4 to the power of D is equal to 1. That is the stopping criteria. Right? So once my data, so what we are saying is that we are keep on dividing the data till the data reaches to 1. Okay. So that is how we calculate the depth. Okay. So at each level, the size of data is divided by 4. So n divided by 4 to the power of D is equal to 1. Right? So, and so every time my data size is, this is n. Okay. So this is n by 4. 4 to the power of 1, n by 4 to the power of 2. So n by 4 to the power of d, at last it becomes as 1. So what we get from here is we take a log both sides. So log of 1 is 0, right? So because of this, we get log n is equal to we get d log 4. This is what we get. So we will get d log 4 is equal to log n, right? So d log 4 is equal to log n. We want to get the value of d, right? So what will be the value of d? D will become log n divided by log 4. D will become log n divided by log 4, wherein log n base 2 divided by log 4 base 2. That is same as log n base of 4. Why? Because of this. You know this thing, right? Log a to the base c divided by log b to the base c is log a to the base of b. Okay, so that is how you get d is equal to log n divided by log 4, wherein for both of them base is 2. Right? So that is why we will get d is equal to log n divided by log 4, which is similar to log n base of 4. Because of this, log a to the base b is log a to the base c divided by log b to the base c. So you get a right hand side here. So log n divided by log 4 is nothing but log n base 4. So this is what you get the value of d. It is important to get this value because we want to finally get the complexity. So why we are saying, why we are doing it? We are representing the depth d in terms of n. Okay. Otherwise, you will feel that what is d? D is not a, D is not a constant. Okay. What we are trying to say is depth d will not be constant. Depth d is log n base 4. That's what we have to get. So these are the steps of recursion tree method. So what we did, we first got the cost at each level and we also got the depth of D. Depth D we found out. What was the use of finding this depth D? Okay, the use was this, right? So this is what we are getting. So we are getting Tn is equal to 3Tn by 4 plus n square is this. Cn square 3t n by 4 like this, it is the tree is going to grow till you reach to T1, right? The question is how many leaves are there, right? So how many leaves are there? How many leaves are there in a complete ternary tree of depth D? Okay. So that's just the same question, right? The question is how many, so one is there, we found out how many, we found out what is the depth D. We found out what is the depth D by applying this simple logic. N divided by 4 to the power D is equal to 1. From this we got D is equal to log n base 4. Please make a note somewhere, students, that you have got D is equal to log n base 4. Now we are trying to find out how many leaves are there. Okay, so the question is, it's a complete ternary tree. That means each node has three branches. 1, 2, 3. So this level we have 3 leaves. Next level we have 9 leaves, right? So how many leaves will be there at the last level? Simple, no? First level, one. If there was only one level, you can say that it is 1 leaf. D to the power of 1. Next level, it is, you can say this is, and here it is 3 leaves. So I think the formula is going to be 3 to the power of D leaves, right? So if I have 3 to the power D means here D is 0. So 3 to the power 0, 1 leaf. Next level, 3 to the power of 1 leaf, right? So 3 to the power of 1 means 3 leaves. Here it is 9 leaves, 3 to the power of 2 leaves. Right? So I guess the formula should be 3 to the power of D leaves. Correct? How many leaves are there? Right? So the question is, how many leaves are there in a complete ternary tree of depth D?
Yes, ma'am.
Right? So 3 to the power of D. So 3 to the power of D is 3 to the power of log n base 4. Right? It is 3 to the power of log n base 4. Okay, now my next question will be that, okay, let me ask that question after a while. We'll make a note of this. Okay, so 3 to the power of D is 3 to the power of log n base 4. Okay, you remember I had told you that from chapter 1 that logarithmic, whatever log logarithmic knowledge we will need, those conversions will be required, right? So that's why I had given a hint. So we will be using one of the theorem here, that 10 or 11 rules were there, right? So one of them we'll be using here. We will see where it will be used. So this is, these many number of leaves are there. So what does it lead to, right? So what does this tells us? This tells us that the total cost that we found out. So what was given to us? It was told to us that we need to find out how many levels are there. We found out that, right, we have D levels, and then at each level what is the cost. So this is the cost at the first level, cn square. This is what you saw. We are going to add up the cost, plus 3 by 16 cn square plus 3 by 16 square cn square plus dot dot dot. Now see this one, right? So what is this? At the end we have said it is theta, right? 3 to the power log n base 4. What is this? Log n base 4 we found out as these are the number of leaves, right? Log n base 4 is the number of leaves, right? So at the end, so why we are adding this, number of leaves? Because we are assuming that at the last level, okay, at the last level when we have reached to T1, okay, when we have reached here, okay, we are assuming that each of the tree, sorry, computing each of the leaf is a constant cost. Let us say it is T1. It is not n square. What we are saying that when we have reached to the last level, let us say we have only one data item, okay, and computing the cost of that data item is a constant cost. We can assume it to be 1. Okay, so what is the cost at the last level? Okay, so we are saying at the last level, the cost is equal to the number of leaves. Okay, that's why we are adding that term. We are assuming that at the last level, the cost is nothing but how many number of leaves are there, assuming that doing calculation for each of the leaf, the cost is 1 or some constant cost. Okay, so that is why, see, this is why we got this term. So we are saying that if the number of leaves are 3 to the power of D, 3 to the power of log n base 4, we made it as theta. Why we made it as theta? Because it is, theta means it is going to be less. It can be, it's at the same level. It will grow. It may grow less also or more also. So with the number of leaves, we are going to add this with recursion tree method. Okay, so now what is going to be the cost? So the cost is going to be the cost at each of the level plus theta of the number of leaves. Okay, because number of leaves, we are saying that the last level we have reached. Okay, this is how we calculate the cost. And now the interesting part is, see, we have found a series, and so we are saying that this is level D. Okay, so one level before that is going to be the level D minus 1, right? So what will be my last term in this series? This last term is going to be 3 by 16 to the power D minus 1 Cn square, wherein I know D is log n base 4. So we need to solve this geometric progression, right? So now this is what we have got. So we will keep this term as constant. So this term we will keep as theta 3 to the power of log n base 4. So now when we calculate this, we get it as Cn square. This is nothing but Cn square sigma I is equal to 0 to this is D minus 1. So we are replacing D with log n base 4. I equal to 0 to D minus 1, 3 by 16 to the power of I. It is that, right? Cn square, if you take a constant, it is going to be 1 plus 3 by 16 plus 3 by 16 square, 3 by 16 to the power of I. And you know the answer for this. Okay, so if it's a geometry, so but you don't know the answer for this, but you know the answer if the limit was I is equal to 0 to infinite, right? Then it's a infinite geometric series, right? But we don't know the answer for this, but we can always say that this term is going to be less than, this term is going to be less than or equal to if this was an infinite series, right? That's because we want to find an upper bound. So we know that if we replace this term with infinite, this is going to be less than Cn square I is equal to 0 to infinite. We have just replaced this term with The upper limit we have replaced with with infinite. And we know the answer when it is infinite. So the geometric progression answer is 1 upon 1 minus r. We know the answer for this. If k is equal to 0 to infinite, x to the power of k is equal to 1 upon 1 minus x. 1 upon 1 minus x. And here x is 3 by 16. Right? So we are going to replace this with 1 upon is less than equal to the cn square, we have put it here, 1 minus 1 upon 1 minus x. X is 3 by 16 plus theta of this. So we are going to get this as 16 by 13. If you do this, okay, if you calculate this, it is going to come 16 by 13 cn square. So this less than term we have replaced with equal to, but we know that this is going to be less than, okay. So this is going to be equal to. Why we are putting equal to? Because we know ultimately we are going to put big O of something. So it is going to be less than or equal to. Okay. So this is going to be equal to 16 by 13 cn square plus theta 3 to the power log n base 4. Right? So fine. There is no problems. Okay, I've got this solution. But I want to know the final answer. Now the competition is between n square and 3 to the power log n base 4. Right? So I don't want to say the answer as Tn is equal to 16 by 13 Cn square plus theta 3 to the power log n base 4. I want to say the answer only in one term. Right? So either it should be n square or it should be log n to the base of 4. It's little difficult to compare between n square and 3 to the power of this. So directly I cannot say that this 3 is what 3 is an exponential term and this is a polynomial. I cannot say that. Okay, I will not say directly that 3 to the power of log n to the base 4 is a exponential term. So this will be more and n square is a polynomial. No, because I will first find out that can I replace 3 to the power log n base 4 in powers of n? Can I do that? Can I represent 3 to the power log n base 4 in powers of n, in n to the power of something? You apply that, the methods we had learned, right? So if you apply that, you will get something. You want to try that out, students? Oh, this class is still 35, no? Till, yeah, we have time, yeah. So the question is 3 to the power of log n base 4. Can I represent it in powers of n?
We can write it as n to the power log 3 base 4.
Very good. Very good. Who answered that?
Vishnu.
Vishnu. Very good, Vishnu. Yes. Okay. So we can represent this 3 to the power of log n base 4 as n to the power of log 3 base 4. Okay. So I had solved this, students, and I had put it here. So how this is from the theorem that we had got, that we had learned. Okay, so the solution is here. You can go through, it's a simple solution. I mean, so what I have tried to prove here is LHS is equal to RHS. So I took 3 to the power log n base 4. Okay, and I got it as log 3 base 4 as same. Okay, so log 3 base n to the power of log 3 base 4 is same as 3 to the power log n base 4. So you can go through it later on. Okay, so that's the solution. So what we do is, so we represent this theta 3 to the power log n base 4 as, we write it as theta n to the power of log 3 base 4. So now the competition is between n square and log 3 base 4, isn't it? So this is n power of n, this is n square, that is n with power 2, and this is n with power 3 base 4. So you must know that, because log 4 base 4 will be 1. So log 3 base 4 is going to be less than 1, right? Log 3 base 4 is going to be less than 1. So obviously n square wins. Now the competition is between n square and n to the power of log 3 base 4. So obviously n square wins in the growth rate, right? So we will call it as So we will call it as ON square. We will call it as ON square because this is given to me as theta term. I want to find out the term which is less than. Okay. So we make it as ON square. Or should it be the other way around? Theta log 3 to the base of 4. Uh, n to the power of, see, log 3 to the base 4 will be how much? Will be less than 1, right? Yes, students? Log 4 to the base 4 is going to be 1. So log 3 to the base 4 is going to be less than 1. Right? It is going to be less than 1. Okay. Yeah, it is going to be less than 1. So, So Tn is equal to 16 by 13 Cn square. So we call it as Tn is equal to On square. So because we want to find the upper bound, which is less than or so it should not grow more than this. The idea is, again, if whenever there is a confusion, okay, we again go with the basic definition that Tn is equal to O of Fn. Okay, for some constant C. That means this should grow. So Tn is equal to O of this means the left hand side should be always less than or equal to the right hand side. Okay, so that is why we are going to pick it as On square. Okay, so now so this is what we got, right? So we got Tn is equal to 3Tn by 4 plus n square. So we are done. We applied the we applied the we applied the recursion tree method, right? What were the steps of recursion tree method? We kept on dividing the tree. Okay, we went to the level where we are having only time complexity of T1. Okay, and we added up the cost at each level, plus we added the number of leaves, right? We also represented everything in terms of the depth D, and then we found out the number of leaves. At total number of leaves, we added that cost and we simplified it and we got the answer. Now what we are saying is we are verifying the solution using our substitution, right? So now we have got the solution is On square. So we say Tn is equal to 3Tn by 4 plus n square. Now, how do we apply substitution? We assume that it is OK square for all k is less than n. And then now I have to prove that it is Tn is equal to On square, which will be easy to prove. Okay, so what we do is we will say that Tn by 4 is going to be On by 4 square. This is what we will assume that this is true because it is true for k is less than n. And n by 4 is less than n. So Tn by 4 is equal to O of n square means On by 4 square. So this is what we put. So Tn is less than or equal to Cn by 4 square. So we put it here, right? So Tn is equal to 3Tn by 4 plus n square, right? So we put it as 3T n by 4 plus n square. Now Tn by 4 we say that it is Cn by 4 square plus n square, which is less than 3Cn by 4 square plus n square. So this is what we get. So we will get, we open it and we get it. It is less than or equal to Cn square if C is greater than equal to 16 by 13. So we try to prove it and you will get a value of C for which it will always be less than or equal to Cn square. Right? So if we find out the answer using substitution tree method and using the recursion tree method, and then we verify the answer using the substitution method. Okay, so we can apply this kind of a method for all the problems for which wherever we have to apply the recursion tree method. Okay, so I will conduct a tutorial, students, not now, after completing the master method also, after unit 1 is done. Okay, I will conduct a tutorial wherein we will take the problems. Okay, so in those problems, I will again give you, some problems to do, and then I will tell the solution also using recursion tree method. Okay, so now we will start with master method. Okay, so I know it's only last, maybe some 7 to 8 minutes, but we can just revise master method and we can just do one example with master method. So everybody likes master method, because once you know master method, you just have to find out what is A, what is B, and you have to put it in three formulas. Yes, you have to remember these formulas, but they are not difficult to remember, right? So once we know master method, we want to only use master method. That has been the trend. Okay, so let us see. So yes, it is important to tell you the complexity quickly. But again, using master method, we may have to do some, you can say, some transformation, because we want to put it in this form. This is what is required, right? So it provides solution to the recurrences of the form. The equation has to be in this form: Tn is equal to A T n by B plus Fn, right? Tn is equal to Atn by B plus Fn. So whenever any expression is given to me, I must first find out what is A, then I should find out what is B, and then I should also find out what is Fn. And then I have to see that whether my condition, my equation given is falling in case 1, case 2, or case 3. So there are 3 cases of master method. What is the first case? The case 1 is, it says if Fn is equal to O of n to the power log A base B minus epsilon, right? Next case says if Fn is equal to theta of n to the power log A base B. And the next case says if Fn is equal to omega of n to the power log A base B plus epsilon. The important is my Fn will fall only in one of these categories. Fn should fall only in one of these categories. That means I have to be sure that Fn is falling in which one of these categories. And here another important point is, so every time this expression is given to me, I need to calculate log A to the base B. And also my epsilon has to be greater than 0. So in the first case, if Fn is O, n to the power log A base B minus epsilon. And epsilon should be greater than 0. At least it should be at least 1, or some value which is more than 0. Not at least 1, it has to be greater than 1. 0, it can be half also, or any value which is not 0. It cannot be equal to 0. And here in the third case, it again epsilon has to be greater than 0. So the first case is simple. If Fn is O, n to the power log A base B minus epsilon for some epsilon greater than 0, then you say that time complexity Tn is equal to theta of n to the power log A base B. Right? So this is what has been proved, by master method. The master method says these things have already been proved. So we just apply the master method. Second case says that if Fn is equal to theta of log A base B, then Tn is going to be theta of log A base B log of n. Theta of n to the power log A base B log of n. Right? So, but we should be able to easily identify what is Fn. Fn is falling in O of this, theta of this, or omega of this. Then the third case says that if Fn is equal to omega of n to the power of log A base B plus epsilon for epsilon greater than 0. And along with that, this condition also should satisfy. A of Fn by B is less than or equal to C of Fn for some C which is less than 1. So if you find that Fn is omega of this, then you also have to see that the other condition also satisfies. Then only we are able to apply case 3. Okay, for C is less than 1, then you say that Tn is equal to theta of Fn. Right? So probably we can see one example, students. Now we have 3 more minutes remaining. Okay, so let us see. So this we will do only through the example. Okay, so let us say this is given to me. Tn is equal to 16 Tn by 4 plus n. Right? So you have to now try out that which case it will fall. Okay, so everybody, you can try out which case it is going to fall. And then accordingly, we will see. Then we know the answer. So here the important part is I want to find out whether it falls in case 1, case 2, or case 3. So you can tell me which case it is going to fall. So whoever gets can tell me which case it is going to fall.
First one.
First case.
Last case, case
First
3,
case.
first case. Yes, it is going to fall in first case. Yeah, how it is? So the first thing is I need to find out. So these are the three conditions which are written here, right? So I need to find out first log A base B. So I need to know what is A, what is B. So my A is A T N by B. So A is 16, B is 4, and Fn is N.
N.
Right, this is given. So now I need to find out what is n to the power of log A base B. So it is going to be n to the power of log 16 base 4. Log 16 base 4 is 2. Right, so n to the power of log A base B is n square. Right, so now and Tn and so so the condition is if Fn is O to the power of this, for checking it for first case, if Fn is equal to O to the power of n log A base B minus epsilon for some epsilon greater than 0. Now my Fn is n, which is, I can say that it is O of n square for epsilon is equal to 1. So when your epsilon is equal to 1, so you can say n is equal to this n square minus 1. So for value of epsilon is equal to 1, we are going to do, we are Hello, can you hear me, students? Hello.
Yes, ma'am. Yes, ma'am. Now we
Sorry,
can.
there was a phone call, so this is another problem, that if I do it from phone, this problem will occur. So I just dismiss, some random call was there. Okay, so if so I have to find out if n is falling in which category. So I find out that n is O of n square, you can say, when your O of n, so and if you put n is epsilon is equal to 1, so it is falling in case 1. So the answer for Tn is going to be theta of n to the power of log A base B. So the answer is theta of n square. Right? So we wind up here for today's students. We will do some more examples of master method tomorrow's class. Okay. And we'll continue with this. Yes. So yeah. All right, students. Thank you very much. Yes. I don't know how many of the students could finally join. Very less. Anyways, all right, students. Thank you.
Thank you, ma'am.
Thank you.